So this is the answers to the homework assignment where we have some complex numbers. The first problem, we've got the square root of -4. In fact, you could just, I'm going to have all these ones done where you can see the answers and you can see how they were worked out. At any time, just pause this video so that you can stare at and look at these answers more closely and see how they're done. In number 12, we see that we have the square root of 50 times the square root of -1. So we have to break up the square root of 50 into the square root of 25 times the square root of 2 times the square root of -1, which gives us 5 root 2i. And this is the answer, 5 root 2i. But convention has us writing it in this way, 5i and then root 2. Only reason is that it's not confused with if you accidentally wrote the I too close, it looks like it's under the radical symbol. But I do want to stress that this is the actual number, 5 root 2 and then the I. In number 13, you were to graph. And graphing complex numbers is slightly different. It's not a real coordinate plane. It's a imaginary or complex coordinate plane where the horizontal or x-axis is where we put the real portion of the complex number. The vertical or y-axis is actually now our imaginary axis, and each one of these units is an I. So this is 1i, 2i, 3i. So this number here has 0 for its real and 2i for its imaginary, so we just go up to 2i and put a dot. The question was also to find the absolute value, and this is no different whether we're in complex or real numbers. Absolute value is talking about the distance from 0. But in complex numbers, what we mean is we mean from the origin, where the real and the imaginary portion are both zeros. And so therefore, we're looking for that distance, which we can see is 2 units. We don't say 2i, it's 2 units because we went 2 units on the imaginary axes. So this distance is just 2 units, and that is the absolute value of 2i. So let's just take a departure for a moment and talk about absolute value of any complex number. Well, we're going to look at it by graphing it first, because it's the easiest way to think of absolute value, this distance from the origin. Because any complex number has an a and a bi. So when we graph it, we are going to go a units in the x direction, in the horizontal, and we're going to go b units in the imaginary, on the imaginary axis. And so therefore we're going to have this distance, this a and then b. When we connect it to the origin, we see that we've created a right triangle. And it's that hypotenuse of the right triangle that is the absolute value. So if we just look at the legs of the right triangle as a and b, the Pythagorean theorem tells us that a squared plus b squared is going to equal the hypotenuse squared. And we don't want to know what this hypotenuse squared is, the absolute value squared, so we take the square root of both sides. At this point also I want to remind you that this is very important because this is a mistake a lot of times. The square root of a squared plus b squared does not equal a plus b. And as an example, let's just look at the square root of 4 squared plus 3 squared. And the question would be, does it in fact equal the 4 plus 3? Well, let's just work on this left-hand side first of all. 4 squared is 16, 3 squared is 9. When you add those together, we get the square root of 25, which of course is 5. And then remember, we started off saying, well, does it equal this? So the question is, does it equal 7? Well, 5 does not equal 7. So this is an example, a specific example why this is not true. It is not true that the square root of a squared plus b squared equals a plus b. That is not what it factors to. So taking all that information, we now know that the absolute value of any complex number is the square root of the a squared plus b squared. Notice not I, it's just the b, the real number in front of the imaginary unit. So if we look at this problem in number 14, it says to graph it and find the absolute value. To graph it, we have our axes that we've got our real portion down here. We see the numbers. I'm counting by 2's. And we have our imaginary axes, and again I'm counting by 2's. And so I go to 5 in the real and up to 12 in the imaginary, and we place the point. And that is the point graphed, 5 plus 12i. The absolute value would be to find that distance, and that distance would be the square root of 5 squared plus 12 squared, which is 25 plus 144. Take the square root of 169, which is 13. And so the answer for the absolute value of 5 plus 12i is 13. And so using this method for the absolute value of our complex numbers and our graphing of them, we can see now that we can find that distance to root 2 for problem number 15. In number 16, we do the a squared plus b squared. We get the square root of 17, and we can graph it, and we know that that distance from the origin to that point is the square root of 17. And in number 17, taking the square root of 3 squared plus negative 6 squared, we get 9 plus 36, and we get, so the distance is 3 root 5. When we go to graph it, we've graphed the point 3 minus 6i, and that distance is 3 root 5. For the next problems, we're going to do some addition where you just add the reals to the reals and you add the imaginary to the imaginary. And so we get these. And this one you say, well, that's only got negative 5i, but you can rewrite that as 0 plus negative 5i if that is more helpful. So you know you have 7 plus 0 and 9i plus negative 5i. So you get 7 plus 4i. This is a subtraction problem. I don't like to leave them as subtraction. I like to change them into addition problems, so I just distribute that negative in there, and then I can add together 12 plus negative 2 and 5i plus I. It's a lot easier to distribute it in, and so I do that every time when I'm going to do subtraction problems. And now we have a multiplication, and granted, with the multiplication, you can use the distribution method, and you can multiply 8 times both 2 and then by 7i, and then the I times 2 and then 7i, and you can do it that way, but I prefer the stacking method where you stack one complex number above the other, multiply straight down, and don't forget that when you get I squared, that's negative 1, so it becomes 16 minus 7. Then you multiply the x to get the complex, is what I was going to say, and then add those all together, and that's the final answer. So here's a couple more of those where I stack them. I go straight down, and then we do the x, and then we collect everything together, and we have the answer. Number 25, well, that's just negative 6i quantity squared, so it's negative 6 times I times negative 6 times I, and you can combine like terms to multiply, so negative 6 times negative 6 is positive 36, and I times I is I squared, but that just means negative 1, so it's 36 times negative 1, or negative 36. 9 plus 4i squared, we could do the stacking method, but remember we learned in binomials that when you have a binomial squared, and that's really essentially what a complex number is a binomial, that you get the first one squared, so I have that here, the first one squared, you get the last one squared, and you get twice their product. So don't forget that you can use the same patterns we learned for binomials with these complex numbers. And when you simplify those out and collect like terms, you have the answer of 65 plus 72i. And that is your homework, all the solutions to your homework.